Good afternoon, everybody. So I'm Patrick, and today I would like to talk about the research I've been doing here in iCeMS since a few years. And I'm interested in nano-pockets and nano-pockets for trapping carbon dioxide. So I would like to start by showing you these 4 pictures, which represent a power plant, a car, a house, and a metal industry. And I would like to ask you if you know what this system or application bear in common. So probably some of you may know the answer is that they contribute directly or indirectly to the emission of greenhouse gases in our atmosphere. And of course, I'm sure you know that these greenhouse gases have a huge impact on our environment, and they contribute to the famous phenomena of global warming, which has huge impact on different aspects, such as influencing water resources, agriculture's impacts on ecosystem, but more generally, there's a huge impact on society and the overall planet. So if you look in detail about what these greenhouse gases are, they're classified mainly depending on their chemical natures. So you will find fluorinated gases around 2%, nitrous oxide, methane, and last but not least, there is a huge contribution coming from carbon dioxide. And as you can see from this graph, the main contribution is actually coming from fossil fuel and industrial processes. And more importantly, there is a continuous increase of the carbon dioxide concentration in our atmosphere. And this is mainly due to the economical growth and the development of new technologies. So there is a problem with carbon dioxide because its concentration is always increasing from year to year. So there is a huge concern about our society, so how can we deal with this carbon dioxide level and how can we reduce it? So what concretely can be used, or what process or techniques can be used to reduce carbon dioxide atmospheric level? Well, first of all, you can apply energy efficiency. So this is just dealing by simply using, for example, very efficient fuel cars or electrical appliances that consume less energy. So this is everything everybody can do. And also, everybody of you can also minimize its own energy consumption just by simple reflex, such as turning off unused electrical appliances. There's also efforts based on development of alternative fuels, so more renewable sources or fuels which have low carbon content. And last but not least, and this is where I'm interested in, it's how we can directly trap carbon dioxide from their emission sources. In other words, how can we trap it for example, power plants, and then store it in a very efficient way? So this is what I would like to talk about today. So how can we capture carbon dioxide from emission sources? Well, there are several techniques that have been developed, and I would like to show you the first example, which is, I call it the old method because it's a long time now, but still it's still very powerful, and this is based on chemical absorption. So in this situation, you will react carbon dioxide molecules in the liquid phase with another molecules, and you would form these new molecules that you can easily isolate. However, this process requires a lot of energy. So you need a lot of energy, first of all, to make this reaction happen, and then you need a lot of energy to recover carbon dioxide afterwards from these molecules. So in overall, there is a huge energy penalty from this chemical absorption. And this is why people are now interested in finding new methods, much more mild conditions, and these are called adsorption methods. So in this case, we're not dealing with the chemical transformation of carbon dioxide, but it's direct trapping into a material. Like you would trap carbon dioxide in your pocket, and then afterwards you can transport it and store it in a very safe way. Of course, from this picture, and because carbon dioxide, is a gas molecule, you can easily think that this is not going to happen in your pocket. So people and researchers have been focusing on developing materials that can actually efficiently trap carbon dioxide. And in the field of porous material, there is very promising materials which are called porous coordination polymers or metal organic frameworks. So these materials are composed of metal ions and organic clinkers. So if you combine these two components, you end up with a highly porous material, highly ordering in a three-dimensional structures. So I call it here a pocket house. And these pockets are very efficient for trapping carbon dioxide because they have the nanometer size. So you can really confine in a very efficient way carbon dioxide in nano pockets. And in addition, you can functionalize these materials to make strong interaction with carbon dioxide. So this is why these materials are now well developed and are very promising for capturing carbon dioxide. So this is an example of one metal organic frameworks that have been synthesized called MOF 177, and this is very efficient for capturing carbon dioxide, and under the same condition it can store 9 times the amount of carbon dioxide that you will store in empty bottle. So this is just to prove you that these materials are very efficient for trapping carbon dioxide. And also when you deal with industrial processes, of course, you can think that the production of gases, is not only one gases, but it's usually a mixture of gases. So from fuel combustion, or here an example of a coal-fired power plant flue gas, you only have 13% of carbon dioxide that is released. And the majority is coming from nitrogen. So if you want to capture this carbon dioxide, you need to have a material that selectively can trap carbon dioxide with regards to other gases. And again, these metal organic frameworks are able to do that. And then, however, there is something you need to be aware when you develop a material. So you always start from developing your material in the laboratory. And you always need to think about what will be the next step of your material. In other sense, you want to have a material that can really find potential application in real life. In this particular case for carbon dioxide, you can think of making very efficient membranes, films, or filters to efficiently trap carbon dioxide. So you need to think of, can you directly use your material, or if not, how are you going to transform it to something useful? In other words, how are you going to process it to an efficient device? And there is a drawback from these metal organic frameworks is that they only exist as solids. So this is how they will look like under microscope on the left. So they look like crystalline, very small crystals. But if you look at naked eye, it's just a powder. So like if you had sand in your hand. In other sense, it's very difficult to use this sand if you want to transform it. For example, if you want to make a bottle with specific shape, or even if you want to integrate it into another device, you have problem of homogeneity and so on. So in other sense, it's very difficult to go from solid to solid device. And this is why these materials have difficulties to be used directly in industries. So our target and our interest is we want, of course, in regard with carbon dioxide, we still want to have efficient material to trap carbon dioxide. But we want to use them, to transform them, to process them very easily in a very cheap and very available way, so that we can have very applicable materials for example, industrial device. So concretely, what we aim to develop is soluble nano-pockets. So nano-pockets, this is why I explained before, nano-pockets are important because they are very efficient for capturing carbon dioxide. So we want to keep this nano-pocket size. And we want, on the other hand, to have these materials soluble. Why soluble? Because there's much more methods available, and easy method that allows you to go from solution to a solid. In other sense, there is much more a method available for solution processing, starting from solution or either transforming or integrating by different techniques. And here I show you some of the techniques that you can do. Of course, you can think of modifying or transforming directly your material in solution, very homogeneous reaction. But you can also think of doing deposition by chemical baths or deep coating method. And you can also think of more, I would say, exotic process, such as using spray coating, two-dimensional printer, or three-dimensional printer. So here you have a high control on the final devices you're making. So our strategy concretely is not to develop porous polymers, but we want to develop porous molecules. So they're called metal organic polyhedra. They're also built up by organic and metallic parts, but they exist as single molecules, in other sense, single pockets. So this allows you to tune them to still maintain this nanopore size, but you can also make them soluble if you tune a bit their composition. So how can we make single pockets? So as I told you, you also make them with a combination of organic linkers and metal ions. But in this particular case, you want to have a single molecule. So you want to design your organic linkers in a way that you would prefer to form a single molecules rather than an extended polymers. So this is the organic chemical point of view. And this have been developed since about 10 years, and we are now able, using organic chemistry, we are now able to synthesize various kind of porous molecules which have different size, different shape, and as for metal organic frameworks, you can also introduce specific functions inside their cavities. So concretely here I show you an example of a molecule we developed in the laboratory. So we synthesized this organic linker, and when you combine it with a metal source, in this particular case copper, you favor the formation of a single pocket. In other words, a single molecule. And this is a part of a crystalline structure, so you can see that we keep, as we wanted, the nanometer size of this pocket, which is very important for carbon dioxide capture. And when you study the solid state properties of this system, you see that it can highly store carbon dioxide in a very efficient way. But also, very interestingly, it has selectivity for carbon dioxide. And this is very important for separation in industrial processes. So now, we successfully design a material that is functional and is a single molecules. So that means you can solubilize. And here's just a picture of the same molecules in solution. So a completely homogeneous solution. So now we can directly apply this solution for solution processing. And here I want to show you an example. That's something we are currently working on in collaboration with a group in Leuven in Belgium. So we are actually trying to print a solution of our materials into various devices. So I'll just show you here a picture of MOP ink. So we successfully prepared an ink which has our molecules dissolved, and we're simply using two-dimensional printer to print these molecules on different substrates. And I want to emphasize here that, as you can see from this picture, we're using a simple printer. So a printer that you probably have in your house or even at your office. So it's a very cheap and very easy way to integrate our molecules into various devices. So this is very important for integration, but there is something else that you can do with these molecules. So this is not dealing with integration, but directly using solution to transform your material to something you can directly use. In other sense, we want to make reaction solution to directly have a materials that we can touch and that we can use, such as membranes or films, without any other support. And these molecules, so the same molecules I showed you before, can still have a reaction site. So that means it can still react with other molecules to form different systems. And in this particular case, you can combine these two molecules to link your nanopockets. So now you order your nanopockets in a specific way by playing with the reaction solution. And concretely, how it looks like, if you do that, you start from a clear solution, so both components in a very homogeneous media. And if you play with the condition, applying a bit of heat, you will end up with something that is not anymore a solution, but more like a solid. And depending on the reaction vessel you do it, you can shape it, so you can have cylindrical shape, you can also make squares, or you can either make it the shape that you want afterwards. So now we have really concretely a solid that is functional, and you can make it the size, the shape you want. So this is very important if you think of directly applying it for more advanced properties. So I come to the end of my presentation. So I hope I convinced you that Nano-Pockets are very promising materials, both for having specific properties in the solid state, but more importantly, to make a very efficient device by solution processing. And this is because we can tune their solubility, and we can use very available method to either integrate them into a device, or you can also directly transform them into something you can use. So we hope that this material can potentially have application, for example, for large-scale membranes and filters. So because they're very easy to make, you can easily think of scaling up your materials to have, for example, filtration columns and so on, and filters. And finally, we hope that, of course, today I was focusing on carbon dioxide, but you can prepare your porous molecules with other properties and still use this solution processing to integrate them into various kind of support. So we hope this solution processing of porous molecules can really be a universal methodology for integrating a very functional system into various kind of devices. And that's the end of my talk. Thank you.